All right, welcome back, guys. So this is part 2. So hopefully we got good numbers for part 1, something close to the density that we were looking for. And part 2, we're also going to find that density of water one more time. But this time, we're going to do it with a different method. This time, we're going to use Archimedes' principle and the force of buoyancy. So before I start explaining all this force of buoyancy stuff, because we may or may not have done this in class at this point, let's do a few of the first things we've got to do. So let's look at our setup first. This is the setup that we have. We've got our fluid here. This is our water. Again, this is what we're trying to find the density of. We've got our stand that we can move up or down. And we're going to move this stand up or down as we start doing this experiment. That'll move up or down in a minute. We've got a force sensor here. This is going to measure our buoyant force. And we've got our object. This is our object right here. So as you start looking at our D2L, the first thing it's going to ask us to do, the first 2 questions, is it's going to ask us to take this object and find the diameter of this circle bottom. We used these vernier calipers last week. Remember we used these last week? We used these big jaws here in the bottom. Again, just like any of our tools, when it's closed, make sure it's reading 0, which in this case it's not. So we're going to press the 0 button. We're going to open up our jaws, and we're going to make sure we measure it like this. We're not going to measure it like this because we're not going to know if we're going to get the true diameter. We're going to measure like this. Close here, and we're going to read a number. So you can see here that we're reading 44.38 millimeters. So we got 44.38 millimeters. We're going to be asked to write that into meters. You guys can do that conversion. Once we've got the diameter in meters, we're going to be asked to find the area of that circular bottom. Well, we know the equation for area, pi r squared. That's the one that's in your little hint section here. So we're going to take that diameter, we're going to find that radius, we're going to square that radius, we're going to multiply it by pi, and we're going to find that area. Again, this should be in square meters when you write your number in here. Okay, so now we're asked to go to capstone page 3. Okay, so now we want to start using the computer. We're going to start using Capstone to actually do this experiment. And again, when we do this experiment is all about Archimedes' principle and the force of buoyancy. So if we haven't done this in class yet, the equation that you will see in class for the buoyant force is this guy right here. FB stands for force of buoyancy. That force of buoyancy is equal to the fluid's density. Well, what's the fluid our object is in? It's in water. And that's ultimately what we're trying to find here. It's multiplied by the volume of the water that's displaced. Now, what do I mean by that? Well, as this object goes deeper and deeper and deeper into the water, you can see that the level of water here is rising up. It's the same idea as if you were in your bathtub at home. You jump into your bathtub, what happens to the level of water in your bathtub? It goes up. Why does it go up? Because I am displacing water when I jump into that bathtub. And then I'm going to multiply this by G. So, the force of buoyancy itself. Again, if we haven't done this in class, you're going to hear me or your teacher say this. The force of buoyancy is an upward force that acts on any object that's in any fluid. So again, this is our object that we're using today, and the fluid is going to be that water that we're trying to find the density of. Well, again, look at the equation here. The volume displaced is proportional to the fluid's buoyant force. That means the deeper this object gets in the water, the higher my buoyant force is supposed to be. If I've got no fluid that's displaced, if this object is completely out of water, like it is right now, then the water isn't given any buoyant force to this. Whether or not you realize it, you guys all know buoyant force before. Think about going into a pool and taking a beach ball. You try to stick that beach ball underneath water, you let go, what happens, that beach ball comes back up. And it's coming back up because of that buoyant force that's acting on the ball. So we're going to be using that buoyant force, and we're going to be changing the depth of the cylinder in order to change the volume that's displaced, and we're going to make a graph out of that in this experiment. So, Mr. Wilf's going to zoom in on this for me, and we can see our object is a bunch of little lines on it. We know now the area here in the bottom, but we're going to be, like we said, changing the depth. We're going to be changing the depth based on these little lines that are written here on our object. Now, if you were to measure these, you would notice each one of these lines is 5 millimeters apart. 0 starting on the bottom, we got 5 millimeters, 10 millimeters, 15, 20, 25, so on, all the way up to 45 millimeters. Okay, so again, we're changing the volume based on the depth. So ultimately what we're graphing here in this lab today is how the depth of that cylinder changes, remember each one of those lines, compared to how the buoyant force changes. So my graph is going to have the depth on the run on my x-axis and the buoyant force on my y-axis. It's going to be my rise. And if you look at question number 1 up here in your lab, the first thing it's asking you to do is to set up the x and y axis. Remember, rise over run is our x and y axis. So the very first thing we're doing is we're selecting the buoyant force on the y and the depth on the x. And again, these are our 2 variables in this lab. These are the 2 things that we're changing within this lab. So, step number 2 says click the preview button. And as soon as we click the preview button, we start getting a number up here for our buoyant force. Right now it's reading minus 1.869 newtons. I don't know if that's right. If I look at my object again, remember what I said earlier. If my object's not in my fluid, what should my buoyant force be? Well, it should be 0 because it's not in my fluid yet. There's nothing displaced because it hasn't had a chance to enter that fluid. So remember, just like every other tool we use, just like our vernier caliper, just like our scale, we've got to 0 our tool before we start taking measurements. And there's a little 0 button that's on our force sensor, which I'm going to press in 1 second. And you can see when I press that 0 button that my buoyant force goes to 0, or at least very close to 0. Our stand's a little wobbly that we have here, so you can see it wobbles around a little bit. But that number is pretty close to 0. Close enough for me. So the first measurement that I'm keeping is going to be that 0, 0 measurement. No depth, no buoyant force. Now I'm going to increase the height of my stand until that water level is at that very first line, that 5 millimeter line. So when I'm at a depth of 5, notice now I do have a buoyant force. That makes sense because now some of my object is displacing that fluid. I'm going to press keep. I'm going to bring it to my next line, 10 millimeters. Notice I've got more buoyant force, which I should because there's more volume underneath water now. Keep. 15. Keep. Okay, so we jumped ahead a little bit. I've got all of my lines and all of my buoyant forces for all of those lines. Again, each buoyant force is higher than the previous one because I'm getting deeper and deeper and deeper in my fluid. I'm going to press the stop button to stop my recording. Up here on the top of my diagram, I'm going to press my scale button, which is going to give me a nice pretty graph. And you can see it kind of looks like a straight line. We're going to go and do a linear graph, which is what a straight line is supposed to give us. And we've got a slope here of 14.4. You want to zoom in on that a little bit so they can see it better? Those lines